In this lecture, we'll dig deeper into the concept of exposure variability and study a few more parameters that are of importance and significance. The first parameter is the exceedance fraction. As the name indicates, the exceedance fraction is defined as the probability that an exposure measurement exceeds a given value. And the value could be an occupational exposure limit or an OEL. Since we are working in the log transformed domain, we can use the parameters of the normal distribution to quantify this. If the geometric mean is denoted as mu of g and the geometric standard deviation is denoted as sigma g, then this probability is given by this formula. This is the probability of xi being greater than OEL, the occupational exposure limit, is equal to the probability of the z statistic being greater than the log of OEL minus the log of mu of g divided by the natural log of sigma g. In other words, it is equal to the probability that the standard normal z value or the z statistic is greater than this ratio, log of OEL minus log of mu g divided by law of sigma g. Pictorially, you can see it in this graph. So again, I'm showing a hypothetical log normal distribution, where on the x-axis you have the exposure in parts per million, the y-axis you have the probability density function, and we have our familiar skewed shape of the log normal distribution. And let's assume in this example that our occupational exposure limit is at 3.5 parts per million. So as we know from our previous discussion, the total area under the curve is 1 or 100%. And we want to find out the area of the shaded part of this, which is the probability curve that is higher than the OEL, greater than the OEL. So if you were to make a single measurement, what is the probability that it exceeds the OEL of 3.5? That is shown by this shaded area. So if we know the exposure group's geometric mean and geometric standard deviation, and we also know the OEL, then we can actually calculate it because of our knowledge of the normal distribution. So from a table of the standard normal distribution, we can determine the area under the normal curve from minus infinity to the z value corresponding to the OEL. And so that would be the probability of the unshaded area in this curve. And so the area of the shaded curve would be 1 minus the P sub OEL. So that is the probability that we are interested in. So again, let's go back to the data set that we have been working with, the data set of 20 data points. And we have already calculated the geometric mean and GSD. Geometric mean is 1.18 parts per million, and the GSD is 2.38. And we are assuming that the occupational exposure limit is 3.5 parts per million. Now, even without doing any further analysis, we can say that in our finite data set, there are two measurements that are greater than 3.5. Okay, so that's the 13th and 14th measurements, so 7.43 and 3.52. So out of a data set of 20, two of them, meaning 10% of the observations, are greater than the exposure limit. But of course, that's a finite data set. What is the actual exceedance fraction? What is the actual proportion of the exposures, the exposure distribution that is greater than 3.5, the OEL? So for this, we need to actually calculate the z statistic corresponding to our exposure limit of 3.5. So this is the natural log of 3.5 minus the natural log of the geometric mean of 1.18 divided by the natural log of the geometric standard deviation of 2.38. And this comes out to be 1.247. And we can then open our standard normal distribution table, and we can find out what probability this corresponds to. So this is the P sub OEL, and it comes out to be 0.8938, meaning that roughly 89% of the area under the curve is less than 1.247. And so therefore, 1 minus this, so roughly 11%, 10.62% of the area under the curve is greater than 1.247. And therefore, we can see that the probability for a single measurement, a single exposure exceeding the OEL is 10.62%. Or 10.62% of the time, we may have an exposure greater than the OEL. And this is a point estimate of the exceedance fraction, and there is an associated uncertainty in this point estimate that we'll talk about in the next slide. But you can see that when you have a large enough sample size, and in this case, we do have n equal to 20 data points. So here, even our, the correct estimate, assuming a normal distribution, is 10.62. And this is actually very close to our, just looking at the data set, we saw that 2 out of 20, that is 10% of the measurements exceeded the OEL. So that's sort of a good check between what the samples tell us and what the inferred value of the exceedance fraction tells us. So now let's look at the confidence intervals for the exceedance fraction. This is shown in this particular graph, and it's kind of hard to read, but let me describe how you would interpret this graph. So in our data set, the point estimate of the exceedance fraction is 10.62, and this corresponds to a z statistic of 1.247, as we discussed in the previous slide. And so if we use a z equal to 1.247, if you look at this set of curves, and you, on the x-axis, you find the z value of 1.247, which is in the far right-hand side, and you find the appropriate curve, which is the curve corresponding to n equal to 20, then you will see that the lower confidence limit around 0.05. I know it's a little bit hard to read of it, but just take my word for this in this case. To find the upper confidence limit, we set z equal to minus z sub OEL, or minus 1.247. And again, so that is in the, sort of in the middle of the x-axis here, minus 1.247. So it's between minus 1 and minus 1.5 over there. And again, go up to n equal to 20, and you will get the upper confidence limit as 0.77. And so the 95th percentile upper confidence limit is 1 minus 0.77, or 0.23. So therefore, the 90% confidence interval is between 0.05 and 0.23, or 5% and 23%. The way to interpret this is that we can say we are 90% confident that the probability of a single exposure measurement exceeding the occupational exposure limit lies between 5% and 23%. We also know that the point estimate is 10.62%. So our point estimate of the exceedance fraction is 10%, but it could be anywhere between 5 and 23%. Thus, if the lower confidence limit, or LCL, is above a certain level, so for example, 5% in this example, we can conclude with 95% confidence that the true exceedance fraction is greater than 5%, or 0.05. You notice that I am switching between the 90% confidence interval, which contains both the limits, 5% and 23%. But if I just want to make a statement about the exceedance fraction above a certain value, we use the 95% confidence value. Uh, so we can say, for example, that we can conclude with 95% confidence that the true exceedance is greater than 5%. Conversely, if the upper confidence limit is less than a certain amount, say 5%, then we can conclude with 95% confidence that the true exceedance is less than 5%. And so this is very useful in determining the acceptability of exposure levels in a work environment. And we can estimate the number of additional measurements needed to lower the upper confidence limit below some critical value, for example, 5%. And as we saw in this example, estimating this is kind of a cumbersome thing, and requires you to be able to read those set of curves very accurately. Fortunately, you don't actually have to do that in the manner I showed you. You will be using this software. It's an Excel spreadsheet that you will have in your course pack, in your course materials, that will do the calculation for you directly. And we'll talk about that a little bit later.